Hey everybody, how you all doing? I just realized I can't hear your reply. Well, anyway, I hope you're doing well. Today we're going to move on with the different types of chemical reactions. Last time it was redox reactions, synthesis, decomposition, and single replacement. This time we're going to do a different kind of reaction with a different motivation. This is called an ion exchange reaction, and the reaction we're going to look at today is called double replacement. The relevant vocabulary for today: soluble means that you can dissolve it into a solvent. For example, salt is soluble in water. Insoluble means it doesn't dissolve at all or only to a microscopic degree in a solvent. For example, sand is insoluble in water. Solute is what you're trying to dissolve. The way it works is the ions are attracted to each other, but the solvent is able to break those attractive forces and break the solute down into its smallest pieces. The solvent is what's doing the dissolving. So in salt water, salt is the solute, I solute you, and water is the solvent. And a precipitate is an insoluble product that will leave the solution. Now, some examples of this would include rain. For example, when the water vapor can no longer be held by the atmosphere, the excess water vapor precipitates out in the form of rain or snow or hail or something else. For these reactions today, the precipitate will be a solid that forms and snows its way out of the solution to form a pile of solid on the bottom of your reaction flask. Ion exchange reactions are reactions which you take two solutions, which means you have two substances which are soluble in water, and then you mix them together in such a way that the positive ion of one solution and the negative ion of the other solution attract so strongly that water cannot break that attraction. And the ionic compound forms crystals which fall out of the solution as a solid. This is what it looks like. When A and B are bonded, water can break the bond. When C and D are bonded, water can break the bond. However, if you mix them together, A and D will attract each other and form a bond so strong that water can't break it. So it forms a solid and falls out as a precipitate. Meanwhile, C and B are still able to be separated by water. That is an ion exchange or double replacement reaction. Now, the way this works, of course, would be where A and D bond together so strongly that water can't pull them apart, and C and B remain dissolved because water keeps them separated. Now, solubility can be determined based on reference table F. Isn't that a lovely reference table? It's not perfect. There are some shortcomings with this table. It's a little bit too, it's either this or this when there's actually shades of gray, but it will get the job done. Soluble compounds, well, any compound that contains one of these ions will be able to be dissolved in water. There are some exceptions to this, though. This first bunch of ions, if these are in a compound, then it will always be water soluble. If a compound contains either of these, halides or sulfates, then the solubility is conditional on what the other ion is. For example, pretty much every bromide compound is soluble, except silver bromide, lead 2 bromide, or mercury 1 bromide. Those would be insoluble and form precipitates. Sulfates are typically soluble, but if the compound is silver sulfate or calcium sulfate or strontium sulfate or barium sulfate or lead 2 sulfate, the compound will be bonded so strongly that water cannot break the bond, and therefore it will be insoluble and form a precipitate. On the other side, if your compound contains one of these ions, then it will not be soluble in water. unless it's combined with one of these ions. You notice that all these insoluble ions are negative. Well, group 1 ions in ammonium are positive, and they're always soluble in water, which is why group 1 ions in ammonium are exceptions to all of these. There are certain additional exceptions. Most chromate compounds will not dissolve in water, but calcium chromate will. Magnesium chromate will. Hydroxide has even more exceptions. Calcium hydroxide, barium hydroxide, and strontium hydroxide will be water soluble to some extent. Most hydroxide compounds won't be. For example, iron 2 hydroxide will not be dissolvable in water because iron is not a group 1 ion and it's not one of these exceptions. If it's soluble, you can use it as a reactant in the reaction. So any of these can be used as reactants. If it's insoluble, then it's the precipitate product of the reaction. So let's see what that means. In this example, silver nitrate and sodium chloride, well, let's see. Nitrate is soluble all the time, so sodium nitrate will be soluble. Silver nitrate will be soluble. Sodium is always soluble, so sodium chloride will be soluble. So there we go, silver nitrate plus sodium chloride. When they combine, the sodium and the nitrate will combine, and the silver and the chloride will combine. So the positive ion of one solution and the negative ion of the other solution will combine. And the negative ion of the second solution and the positive ion, positive and the negative, right, they combine as well. So the Na and the NO3 combine. Now, it's important also to look up charges to make sure you have a proper formula to drop and swap if you need to. In this case, we don't. So this is a completed reaction. Which one is the precipitate? Well, sodium is always soluble. Therefore, it will never be part of a precipitate. So NaNO3 will remain aqueous. Chloride is usually soluble. However, it's bonded with one of the exceptions, and therefore, since silver chloride is insoluble, that will be the solid precipitate, where the soluble sodium, that will be aqueous. And that's a double replacement reaction. Here's another. Calcium nitrate plus potassium phosphate. Once again, the positive ion of one solution will combine with the negative ion of the other. So A will combine with D. So calcium will combine with phosphate. C will bond with B. C will combine with B. So potassium will combine with nitrate. Now, we can't just leave it at that. And again, you may be tempted to write K3NO32. Don't do it. Look up the charges. And based on the charges, potassium nitrate's formula is KNO3. Deal with these numbers after by balancing. Calcium is +2, phosphate is -3. So simply drop and swap to write the formula. And then you can balance. But first, let's identify the precipitate. Nitrate is always soluble, so any compound with nitrate in it will be soluble. So KNO3 will be aqueous. Phosphate is insoluble. Now, not all compounds with phosphate in them are insoluble. For example, sodium, potassium, lithium phosphate will be soluble, and ammonium phosphate will be soluble. But we don't have any of those. We have calcium phosphate, which is not an exception. Therefore, calcium and phosphate will bond together too strongly for water to break apart, and therefore form the solid precipitate. Now let's balance. We have 3 calciums on the right, so we put 3 calciums on the left. We have 3 times 2 is 6 nitrates. We have 1 nitrate, so we put a 6 in front. We have 6 Ks on the left. We have 3 Ks on the right, so we put a 2 in front, so there's 6 Ks on both sides. We have 2 phosphates on the left. We already have 2 phosphates on the right, This is one seriously balanced double replacement reaction. Here's an animation to show you how this works. We're going to react lead nitrate and potassium iodide to form potassium nitrate and lead iodide. You'll notice that the ions are freely moving around. The bonds have been broken. And if we pour the two solutions together to combine them, and then we zoom in really closely to see what's going on, let's find a place to zoom in here. There we go. And let's zoom in. We're going to notice that we have a bunch of ions just floating around. But as a lead collides with an iodine, it will form an insoluble precipitate, which will fall out of the solution, leaving the potassium ions and the nitrate ions floating unbonded in the solution. So what we end up with is, at the very end, if we zoom out, is a layer on the bottom of solid lead iodide, where the potassium nitrate occupies the solution above. And that is a typical double replacement reaction and what a precipitate would actually look like. Now, what if we want to make a precipitate? What if, let's say, we want to make calcium carbonate? Well, what we need is a soluble calcium compound and a soluble carbonate compound. React them together, and the calcium and the carbonate will combine to form calcium carbonate. So we need a calcium solution and a carbonate solution. So let's look at reference table F. Let's find a negative ion that will be soluble with calcium. Well, let's see. Nitrate is always soluble. So let's bond nitrate with calcium. Now, why choose nitrate? Because it's negative. Remember, negatives and positives will form compounds. You may say, oh, group 1 ions are soluble, and bond this with, let's say, sodium. But sodium is +1. +2 and +1 will never bond together. So if you want to make a solution with a positive ion, you better find a soluble negative ion to combine it with. Now, of course, you want to drop and swap to write a formula. Now, what about carbonate? Carbonate's trickier because carbonate's insoluble. You want an exception to that because you want our first substance to be soluble. So let's find a positive ion that will be soluble with carbonate. Well, we could use ammonium or any group 1 ion. So we could choose lithium carbonate, sodium carbonate, potassium carbonate, rubidium, cesium, or even francium carbonate, although as we specified, there isn't enough francium in the world to make this practical. Or you could use ammonium. For the sake of this, we'll use potassium, which is +1. And when we drop and swap, gives us K2CO3. These are the reactants that we can use to make our desired product. But not only are we going to make the precipitate, we are also going to write the formula made from the spectator ions. Now, wait a minute. I thought spectator ions don't change charge. And in double replacement reactions, nobody changes charge. Well, here's the deal. For redox, the game was to change charge. So whoever's not changing charge is the spectator. In double replacement, the rules of the game are different. In double replacement, the name of the game is forming a precipitate. So whichever ions are not involved in that, those are the spectators. So the potassium ion and the nitrate ion are the spectators. Remember from the animation how the lead iodide settled out, but the other ions remained in solution and just watched it happen? So the spectators in this case are the ions that are not involved in making the precipitate. They're the ions that remain dissolved in water. Now let's balance this reaction. We have one Ca on the left, we have one on the right. That's good for now. We have 2 nitrates on the left, we have one on the right, so let's put a 2 there. We have 2 Ks on the right, but we also have 2 Ks on the left. We have 1 carbonate on the left, we have 1 carbonate on the right. Now, you might say, but don't we have three carbonates? No, because then that would be parentheses three, just like we have two nitrates because it's parentheses two. So we have one carbonate on each side. This reaction is balanced. Hallelujah. Now, some prime examples of differences between the redox reactions and ion exchange reactions. Redox reactions are motivated by differences in how much different species are attracted to electrons, whereas ion exchange reactions are motivated by the formation of an insoluble precipitate. Redox reactions involve changes in charge from one side to the other. In ion exchange reactions, there is no change in charge. Otherwise, we would have labeled it under redox reactions. In redox reactions, the spectator ion is the species that doesn't change charge. Whereas in an ion exchange reaction, the spectator ion is the one that doesn't make the precipitate. Because the rules of the game is different, the definition of spectator will be different as well. Now, what's the same about them? They both take reactants and turn them into products, and both require writing formulas based on charges found on the periodic table. And there isn't enough room to put this here, but they also both involve you having to balance them once you've completed writing all your formulas. And that is double replacement reactions. I hope you've gotten a lot out of this. And until next time, when we do stoichiometry of reactions, ooh, that sounds like fun. Bye.